My name is Bronia, and I'm with my group mates. And this is basically our project. A group software engineering, machine learning 34. Our group title is Machine Learning Architecture for Smart Mechanic Matching using binary classification for service records in Uganda's informal automotive sector. The keywords that align with this project are binary classification due to our tabular dataset, collaborative economy, pushing from rule-based to model-based predictive-based predictions, and gradient boosting, predicting modeling, and random forest recommendation systems, and of course tabular data, which is all about our dataset. Presentation covers the background, problem, the research objectives and contribution, methodology, dataset analysis, experimental results, the sharp explainability model selection, and the live demonstration conclusion. Background of our product, the product we're building, is more of Uganda's vehicle repair industry, which is largely informal. Most mechanics work on roadside garages without formal training or even certification. And when a driver breaks down on a Kampala traffic or in a rural road, there is no reliable way to find the right mechanic for their specific problem. Matching is done entirely through a word of mouth, that is proximity. You ask around, they tell you there is a nearest garage, or if else we don't know or we are not sure, or you just have to move until you find one. And the result is overcharging, repeated repair failures, and a deep trust deficit between drivers and the mechanics. So this problem is specifically severe for border riders whose entire livelihood depends on their motorcycles and their motorcycle being roadworthy. And here, our platform, which is now currently we named it MotoFix, it comes out or addresses this through a machine learning system which predicts whether a given mechanic is a good match for your service or specific service request, and which results into our problem statement, and it is in the domain of an informal mechanic matching. Our computation problem here is a supervised problem, binary classification. Like given certain features from a service record, the model predicts a good match, which is a 1, or not a good match, which is a 0. Some of the research objectives here is to train and evaluate 8 binary classification models, and which of these ones, some of them we have already finished. These classification models to apply a sharp explainability to identify dominant predictors. 3 addresses class imbalances through cost-sensitive weighting. Deploy the best model as a live prototype online. So, and some of our research contribution match those objectives. So we uncovered the accuracy paradox of the naive bias of 0.6 and the accuracy of 0.02 recall, which is useless. Deploying, we have tried out a test deployment of logistic regression of F1 score of 0.4 as a live streamlined prototype. So Sandra, you can take it up from here.
Talk about the methodology of our project. Originally, our dataset has 2 million records, and then we picked a sample of 50,000, and after our data cleaning, we removed 15 sparse columns and then we retained 13 features. Categorical features were label encoded. We used the 80-20 method, whereby the 80% is for training and the 20% is for testing. All our models were tested and evaluated, and for our dataset and EDA, from the well-balanced sample, where the service types were roughly 14%, then the agency levels were 33% each. Then the technician rating had a mean of 3.002, and which is a good one because we were using a 1 to 5 scale. We engineered our binary target variable using a threshold of 3.0 rating or above 3. So a rating at or above 3 became a good match, which was 1. Then a rating below 3 became a bad match, which was 0. This produces a class split of 61% good match and 39% good match. This is called the mild imbalance, and this was addressed using class weight balancing across all the applicable models. For our model comparison, regression achieved the highest F1 score, 0.4256. Recall value it had was 0.4608, and it trained in only 0.56 seconds. Then the XGBoost was second, and it had an F1 score of 0.4177. And the Random Forest followed at 0.3747. So the right chart shows the training time. Then the one on the left shows the performance metrics for all the models we're having. SVM took the longest time, because it took 742 seconds. Those are over 12 minutes. So this was ranked in the 5th position. Its F1 score was a 0.3151. Accuracy paradox. The naive bias is our most intrusive failure. It had a high accuracy, but then a low F1 score. Its accuracy was a 0.607, but its F1 score was a 0.047, and it had the recall value was nearly zero, because it was a 0.025. It predicted a not good match for the 99.5% of all the test records. So it only identified 96 of the 3,891 actual good match cases. So in a real world case, if we were to choose a model to deploy, this wouldn't be a good one. SVM had the worst performance. It took a lot of time to be trained. The confusion matrix, all 8 models are shown. 8 models are shown here.
Thank you, Naisanga. So I'll start with the SHARP explainability analysis for the logistic regression. So we applied SHARP to all the 3 best models. Logistic regression, the total cost is 0.126, and the estimated cost is 0.112. Everything else tracks sharply. So our linear model found the cost to be by far the strongest signal. So the next one is the XGBoost. This one is a bit more balanced. So the total cost is 0.182. The estimated cost is 0.152, but the mileage at service emerges as a meaningful third feature at a cost of 0.113. XGBoost found more complex patterns across more features, so it was consistent with its gradient boosting architecture. Then next we have the Random Forest. This one showed an interesting divergence with a service duration hours emerging as the second most important feature at 0.0041, and this is not seen in any other the 2 models. So the key insight across all the 3 models is that cost features dominate because they correlate with rating by construction in the synthetic data. It's not because that it genuinely determines the quality mechanics that we want in the Ugandan informal market. So the system needs GPS proximity, specialization match, and verified reviews to generate sharp profiles that reflect real mechanic matching signals. So next we have the architecture, the decision trees. It has a depth of 10, and we use the GNI impurity at each node. Then other architecture we have is the neural network. Despite its complexity, it achieved an F1 score of 0.2702. It had 13 input features, which are 13 neurons, and they passed through the 64 hidden layer neurons. And then we also had the second layer that had 32 neurons, bringing us to an output of 1. This one was lower than the logistic regression. It does not guarantee better performance on tabular data with limited signal. From all the models, we selected logistic regression, which had the highest F1 score of 0.4256. And then the best recall we have for the logistic still, we have 0.4117. 4608. Test training time was 0.56 seconds, which enables frequent training on a live fixed transaction data. It's highly interpretable and the weights directly explain feature contributions. So we deployed via the JobLead serialization on the Streamlit Community Cloud. And the link to the live prototype is down there in the slides. So this is our deployed prototype on Streamlit. So it takes in 13 features: vehicle type, service type, agency level, and so on, as you can see them up to checking whether the warranty is valid or not. So after that, now when you test it, let's say the total cost is 150 USD, estimated cost is 140 USD, and the service duration is 2 hours. Car's mileage at service is 50,000 kilometers. And here we don't have the tow distance because in this scenario, the car is not being towed, but it's being fixed. Then there's no insurance claim and there's a valid warranty. So we predict the mechanic from here. See? So probability of getting a good mechanic is 50%, 0.4, and not getting a good mechanic is 49%, 0.4. So this mechanic can be recommended. So here I also have an input summary showing all the entries that we had put, but they are not persistent. We would simply add a database in the feature prospects, add a database to the back end to store the summary of all the orders made by that person. In conclusion, still, our best model is logistic regression with the F1 score of 0.4256. XGBoost was second with the F1 score of 0.4177. Nextbase had an F1 score of, it had the least F1 score, which was 0.02. It had an accuracy of 0.07. It had the highest accuracy, but accuracy was not our metric in this instance. Sharp reveals like cost features dominate, especially on the synthetic data limitation. So our limitations were, we were using synthetic data. It had over 2 million records, but we used a sample of 50,000 records. So we actually need to use real Ugandan data. And also it has a cold start problem on newly onboarded mechanics with no transaction history. Therefore, it cannot be rated reliably. So the counteraction plan for the cold start, we want to implement multi and bandit exploitation to route jobs to new mechanics. Then for the synthetic data, we want to validate on live database transaction data via strict A/B testing before the launch. And then for the cost dominance, you want to enrich the features with GPS proximity, specialization tags, and real customer reviews. Next steps, we want to collect real Ugandan transaction data through the MotorFix platform launch, and then implement chronological walk forward split on live time-stamped links. And then we also want to add GPS proximity, specialization tags, and real customer reviews as features. So also want to implement the multi and bandit framework for fairly new mechanic routing. I want to deploy the model as well as a fast API microservice on the MotorFix production backend, thanks to our supervisors, Dr. Gali Wango, who is a supervisor from the Department of Computer Science, and also Dr. Eunice Efrance Namgeni for all the detailed feedback that has helped us improve our work. So also much thanks to the owners of the cargo dataset, the motor vehicle repair and towing dataset, and also much thanks to my fellow group mates